Questions about anything?
No. Next time.
So I like this section we're to do the next couple of days. Suddenly I'll be able to solve a whole bunch of pretty fascinating questions, computing famous integrals. You'd be surprised how many integrals are out there. The values are known to be very simple expressions involving pi and e and things. And the way that those things are computed are via something called the residue theorem. And we can do a lot of things with the residue theorem in a very simple situation. Stein invented a word, as far as I can tell, of toy regions. And so we're going to do an I'll call it a baby residue theorem. It's more of an elementary residue theorem. We'll have a much more sophisticated residue theorem later, and we're going to apply it on toy regions. And I can explain it completely today in a few words. So for us, a toy region is going to be a simple closed curve consisting of lines and circles, pieces of lines and circles, like that one there. That's called a keyhole domain. You notice the little keyhole punched out there. And so these toy regions are simple enough that you can just see the Cauchy theorem on them. So maybe Stein has a more precise definition of what he thinks toy regions are, but my definition is you can cut it up and see the Cauchy theorem. So for example, in that keyhole domain, I take a couple of those purple cuts, and then you realize, oh, the integral around gamma is a sum of three integrals around a closed contour. Namely, you go around, say, this top corner one here, follow the green curve around, and then when you get on the purple curve, take the curve going this way. Then when you do the next one, you take the curve going the other way, hop on the green, take it going this way here, continue on the green. That's a closed curve in the counterclockwise direction. And then finally the third one, same thing, except this time you go the other way on the purple cut. And when you draw those arrows, you always get arrows that go one way and back on the purple cuts. They cancel when you add them up. So the integral around gamma would be the sum of those integrals. And not only that, but if I cut it up in a clever way there so that I could stick in convex open sets. So if the function I'm integrating is analytic in a slightly bigger open set, I can squeeze in those convex open sets like I've drawn there. The orange one is convex and open and contains the top right closed curve. And the blue one is convex and open set containing the bottom right closed curve. And finally, the one more green one there contains the left one. And so the fact is, if f is analytic, f is analytic inside. Have I said what I mean by inside and on? In this, if f is analytic on an open set, containing gamma and it's inside, usually you can just see the inside. I'm not assuming the Jordan curve here because this is such a simple thing that you can see the inside and the outside. So f is f analytic on an open set containing gamma and it's inside. Okay, that's a topological term, but we all know what it means. Then the integral around gamma of f equals 0. And you see that by adding up those three things and using the Cauchy theorem on a convex set. Okay, so that's what toy regions are. Questions about that? Another example maybe that's a classic thing that we're going to apply this to is this one. I take a I'll do two of them. This one's a very common one to apply it to. That one's, I can just do one convex set there and apply Cauchy theorem on a convex. Another one we're going to do is this one where we take a little bite out of it, usually at the origin. Let's see, we didn't want to go through the origin here. So there's usually a singularity at the origin. That's how we take a bite out of it. And to get convex open sets, let's see, I would take a cut. Let's see, I'd go this way down, this way going on this side. And then to get a convex open set, I'd take, let's see, this is a convex open set. I'd take a little bit bigger thing like this. That would be a convex open set containing the right-hand side of that thing. And then this convex open set would be one. And of course, I could squeeze those down as close to the green thing as I want. But usually we're dealing with functions that have a finitely many poles, and the green, it's analytic for miles and miles outside of that region where the poles occur. That's where we're going to apply this thing. Okay. This convex open set would be easy. In fact, I could just take a slightly bigger semicircle like that. Okay, so here's the baby residue theorem on toys that I'm going to apply today. Okay, so I'll draw a picture. I'll have this toy region. How about this? And then I'll have finitely many places where there's poles inside. A1, A2, out to AN. And let's call this thing gamma, curve gamma. And so I'm going to assume that F is analytic on a bigger open set. So maybe it goes like that. So F is analytic on a bigger open set except at finitely places where it has poles. Except at finitely many places where it has points. Inside gamma where it has poles. In the future, we're going to allow essential singularities at those points. So the baby residue theorem requires them to be poles. Okay, and then the theorem is that the integral around gamma of f dz is easy to calculate. It's just 2 pi I times the sum of the residues. So that would be j equals 1 to n of the residue at aj of f. And I'll refresh your memories about what I mean by the residue. Question about that? Well, the proof is a snap. Let's let RJ, let's say, remember how RJ of Z is the principal part. Remember, it looked like an AN Z minus AJ to the N plus blah, 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 plus down to a1 over z minus aj. And the residue term was this a1 term. That's the residue at aj of f. So that's going to be the principal part. Of f at aj. Then we saw this when we did the partial fractions proof using Liouville's theorem. If I subtract all the principal parts, so f of z minus the sum of the principal parts there is actually analytic. Inside, it has removable singularities. For example, at aj, I would subtract the rj first. F of z minus rj has a removable singularity, and all the other rk's with k different than j are not singular at aj. So they would actually be analytic at aj. So that's how you see. You pull it into two pieces like that, like I did in partial fractions. So it has removable singularities at the AJs. So by giving it the proper values, at AJ and applying the Cauchy theorem, which we believe holds because we can just see it on the toy region. Well, let's see, that means the integral of that function would be a big fat 0. So we'd get 0 equals the integral around gamma of f dz minus the sum, when I distribute it, of the integral around gamma of rj dz. And this thing is interesting to think about. When you look at rj, this is going to be 2 pi I times a1, the residue. And that's going to be very easy to calculate. The residue at aj of f. And that's going to give us the residue theorem. And here's the reason why. Remember what RJ was. Maybe I'll just copy it. Here it is. Guess it's not bad to keep that. If you look at, that's the RJ, and now I'm going to integrate each one of those terms. These terms are derivatives. This one's not a derivative of something, because it would require a log function to calculate. So this is not a derivative of something. But this one is, for example. This one would be d by dz of an over z minus aj to the minus n plus 1. This would be, you know what it is. I'm not going to write it. This is a derivative. So all other terms are derivatives of something. And so the fundamental theorem would say that those integrals integrate to 0. So all others are derivatives. They integrate to 0 by the fundamental theorem of calculus, because that's a closed curve. And so we see that the integral of, let's see, I need to see why that integral of the A1 term is. So now I would have the integral of Rj dz around gamma would just be the integral of A1 over z minus Aj. And I claim that's A1 times 2 pi I. And I didn't use log the first time I showed you this, but it turns out to be, you can use the log function to see y. Here's another y. Let's see. I've got my curve. Pick a point, let's see, here's my AJ over here somewhere maybe. I can see with my eyes that I can find an A over here. Let's call this an A. I have an A there such that if I take a branch cut that goes out, let's say like this, it crosses the curve in exactly one point. So this branch cut crosses gamma in exactly one point. And it does so nicely, transversely, makes an angle there and everything. Okay, so that's the branch cut I'm going to take. Let's call this angle alpha right here. That's going to be my alpha. So I'm going to take a log alpha branch. And so now let's see, here's how I'm going to do that. I'm going to slide in 2 points. I'll call this one A and this one down here B. I'm going to slide A down to that branch and I'm going to slide B up. Okay, so I'll write this h of A is equal to integral around gamma of 1 over, let's see, what am I doing? 1 over z minus A dz. Okay. And that's equal to the limit as A slides down and B slides up. Of the integral, I'll say, I'll take the curve that starts at A and goes around gamma and ends at B. So that's going to be the curve that starts at A and ends with B of 1 over z minus A dz. And in that region, the log function is analytic. And we know the log function is an antiderivative for z minus A. So this is going to be an integral. It's going to be a limit of the integral of that piece of the curve. And I can have d by dz of log, that branch of log, of z minus A. As I slide A down and B up. And of course that's going to be a limit of log A B minus A minus log alpha, did I say A? I meant alpha. Log alpha A minus A. Okay, and those things are, that's going to be natural log of the modulus of B minus A plus I times the arg alpha of B minus A. Let's see, what is arg alpha? Let's think about it. B is, that's going to be 2 pi, it's going to be something like this. That looks like 2 pi plus alpha minus something small. Minus epsilon B. Minus epsilon B. Some small thing. Okay. Then we'd have minus log modulus A minus A plus I. That would be alpha plus a little dinky something, epsilon A. And in the limit, oh, I should leave the limit here. As those slide, of course, B and A tend to the same point. So those log terms cancel each other, ln terms. And then those little epsilons tend to 0, and I'm left with 2 pi plus alpha minus alpha. So this would be equal to I times 2 pi minus alpha plus alpha. And that's 2 pi I. So the other ones integrate to 0 because they're derivatives of something. And this one we can calculate now using log. Okay. Let's say I calculated it once at only one point, but recall d by dA of h of A is equal to the integral around gamma of d by dA of the inside That was problem number 1 way back. And that's equal to the integral around gamma of 1 over z minus a squared dz. And that's the derivative of something with respect to z. That's equal to the integral around gamma of, what is it? D by dz of minus 1 over z minus a. And so that's a big fat 0. And so h prime of a is constant on the inside. I mean, h prime of a is 0. H prime identically equal to 0 implies h is constant. Inside gamma, and that constant is 2 pi I times the residue. What is it? I calculated it A, but it's got to be constant on the inside.
I think h of a is constant, just 2 pi I, and then we just factored out the residue earlier.
Oh, yeah. Psh, that's what I'm trying to prove. Okay, so that's the baby residue theorem. Now I'm going to start playing games with it and showing you how sort of powerful it is. Questions about it?
I have a quick question.
Yeah.
Earlier, what exactly is like the gamma from A to B?
It's the part of gamma that starts at A and goes around and ends at B on gamma.
I see. It goes the other way. Okay.
Yeah, it goes around the long way. Because you can't go across the branch cut. That's why I'm avoiding the branch cut. So I guess it's worth pointing out starts at A, follows gamma, ends at B. Okay, so here's a first application of this thing. We can calculate rational integrals, or integrals of rational functions. So let's suppose P and Q are polynomials. They could have real coefficients typically, or polynomials, complex polynomials of Z. And let's see, I need the degree of Q to be at least 2 bigger than the degree of P. Q is going to be in the denominator. And so the integral I'm looking for makes sense. I need Q to have no zeros on the real line. Then the residue theorem is going to spit out that the integral from minus infinity to infinity of P of x over Q of x, so this is a real integral, is 2 pi I times the sum of the residues at, I'll put here A, residues at A of P of Z over Q of Z. And this is, I'll call these where A is in the set of zeros of Q in the upper half plane.
Would that be P of A over Q of A?
No. The residue is at A. P of Z over Q of Z is the function. So P of Z is Q of Z is a function, and you can calculate the residue at A, where A's are the zeros of Q. That's where the thing would have poles.
I guess I'm confused. What is the value of Z?
That's
Okay.
the function of Z. It's just emphasizing that it's a complex function of the variable Z. Yeah, it's kind of traditional notation. I guess I could quit that. I don't have to have that there. So I should tell you that where Z, Q plus is equal to the set of zeros of Q in the upper half plane. And in the, I don't know if I've used this before, but I'm always going to refer to the upper half plane as UHP. And of course the lower half plane is LHP. Okay, so the proof is going to be a snap. Let's see, proof. I'll use that contour like I've drawn before. It's the simplest one where I take a half disk, and I'll go out to some radius r and have minus r here. And I'll make sure that that r is big enough so that those finitely many zeros of Q in the upper half plane, they're finitely, we know because the fundamental theorem of algebra. So let's make R big enough that all of the zeros of Q in ZQ plus are inside this is my gamma. Sometimes you could call that gamma R since it depends on R, but I'll try to streamline my notation. Okay, That's one restriction on my R. Notice that if I parameterize the real line part, I parameterize by z of t equals t. And of course, z prime of t would be 1 then. And so the integral around R is I sub R is exactly the integral I want. That would be the integral. Let's see, the t would go from minus R to plus R. So that would be the integral from minus R to plus R of P of t over Q of t, and that's the integral I want. Let's see, the z prime of t is 1, so a 1 here. That's something I want. It turns out the integral around the circular part, so I'll call this part I sub R. I'll call this circular part C sub R. Okay, I don't have to parameterize it, but I know the C sub R would be parametrized by z of t equals R e to the it, as t ranges from 0 to only pi. I don't have to parameterize, though. I'm going to use the basic polynomial estimates. So I claim now that the integral around C sub R, P over Q dz, tends to 0 as R goes to infinity. Let's see, what should I say here? R big enough that all the zeros are in Q. Let's say that R is bigger than, I'll call that R sub 0. And the key is the basic polynomial estimate. So remember what the basic estimate says. Let's see. We would have a z to the degree of p is less than or equal to p of z is less than or equal to capital A times mod z to the degree of p. And that would be if mod z is bigger than some radius for p, the p function. And then we'd have another one of these things, az degree of q is less than or equal to q of z is less than or equal to b z degree of q, and that's if mod z is bigger than rq. Okay, and p is in the numerator. So I told you lots of times that this is the numerator estimate because it bounds p by something, but q is in the denominator. And so this is the denominator estimate that I need for Q. And so when I get my integral around C sub R of P over Q dz is going to be less than or equal to, let's see, the maximum that P can be on that thing. Let's see, max P over Q on C sub R times the length of C sub R, which is, what is it, pi r, not 2 pi r, half of a circle. And let's see, that's going to be less than or equal to a times r to the degree of p over little b times r to the degree of q. If I have r big enough, I'll tell you how big I need it to be. And let's see, this is gonna, I claim this is going to be less than O times pi r. So let's see, that's equal to a pi over b times 1 over r to the degree of q minus the degree of p minus 1. And that number in the exponent there is greater than or equal to 1. It could be equal to 1. Because remember, the degree of Q is at least 2 bigger than the degree of P. So that first part's at least 2, and I minus 1. So that's bigger than or equal to 1. And so here's something I'd like to be careful about. That is strictly less than a pi over b times 1 over r. And the important thing is here, when r is bigger than 1. Why is that? Because if r is bigger than 1, then r to the n plus 1 is bigger than r. What do I want to do here? Yeah, I don't want to do that. Just think about that. And so that's going to go to, I claim that this is going to go to 0. Well, let's see, what do I need? When r is bigger than the max of r naught, so it contains all the zeros in the upper half plane of q. I need rp and rq so that the other inequalities hold, and so that very last inequality holds. I need it to be bigger than 1, which is kind of a no-brainer. I'm always thinking of r as gigantic. And so we see that the integral around c sub r tends to 0 as r goes to infinity. Okay, and so now when I apply the residue theorem, what do I get? Residue theorem tells me the integral around gamma, that's equal to the integral around the I sub r part, plus the integral around the C sub r part. That's equal to 2 pi I times the sum of the residues. And now I let r go to infinity. This one tends to the integral I want. Call it I. This one tends to 0, and I get that the integral I want is equal to the sum of the residues. So if I was going to do this right, I would go back here. I never wrote down the integral I want. Here it is. I. That's the integral I want. And by the way, the fact that the basic polynomial estimate shows that the integral decays like 1 over x squared for big X. That integral has a, what's that called? It converges. It's an absolutely convergent integral. So there's no sweat about letting that r go to infinity. But that falls out from this argument. If I integrate around a symmetric thing, I get this value. And when an integral is absolutely integrable, that symmetric thing tends to the actual integral, the actual area under the curve. So I guess maybe I should write that out. Note. We would have the basic polynomial estimate shows that p of x over q of x is less than or equal to a constant over x squared for x bigger than something. Shows that integral is absolutely integral. Shows that integral is, by comparison, with the famous integral from 1 over x squared. So if your freshman calculus class would have shown you that the integral from minus r to r tends to the actual integral as r goes to infinity, and the actual integral makes sense. So now that we know these facts, the hard part of computing these things is doing the algebra to compute the residues. And it really is just algebra. So I've reduced computing these integrals to just doing algebra. And so in the next couple lectures, I'm going to be showing you some tricks for computing residues. One of my favorite examples that I always do first, I want to compute the integral from minus infinity to infinity of 1 over x to the 4th plus 1 dx. Let's see. So step 1 is find those roots. Find the 4th roots of z to the 4th plus 1 equals 0. Let's see, from the 4th roots of minus 1. It's something you probably learned how to do someplace a long time ago. They're e to the I pi over 4, e to the I 3 pi over 4. Those are in the upper half plane. And then the ones in the lower half plane are e to the I 5 pi over 4 and e to the I pi 7 pi over 4. So these are in the upper half plane. And these two are in the lower half plane, so we don't care about these. We don't care about the ones inside the curve. And so then my integral, by the same calculation above, my integral is going to be 2 pi I times the sum of the residues. So the residue, they're only going to be 2 e to the I pi over 4 of f. And the other one is the e to the I 3 pi over 4 of f, where f of z is equal to 1 over z to the 4th plus 1. Okay. And so let's think, if you just did this problem for the first time, let's call these roots R1, R2, R3, R4. So I'm thinking now today, or at least pretending to think, I'm going to do a bad idea. And you'll see why it's an idea that works, but it's a bad idea. So near the root R1, let's say, we have our f of z would be, I could factor it. So it would be z minus R1 times z minus R2 times z minus R3 times z minus R4, etc. 1 over that. Okay. And I can pull out the 1 over z minus R1. And then what's left there is 1 over the product of z minus rk, where k is unequal to 1. That's analytic near R1. So it has a regular power series. let's call it h of z. H of z, it's analytic near R1, and it would have a power series expansion, A naught plus A1 times z minus R1 plus etc. And when I multiply through, this is the algebra part, I would get A naught over z minus R1, and all the rest of those things would be a regular power series. Okay? Plus regular power series terms. In powers of z minus R1. And so this is the residue term. So A naught is the residue at the root 1 of my f of z. And let's see, that A naught is the value of capital H at R1. Remember, I wrote down what H was up here. It's that thing. There it is. So that's going to be equal to 1 over R1 minus R2 times R1 minus R3 times R1 minus R4. That's ugly looking. And I have to add up two of those ugly looking things and do an algebra and clean them up. Anyway, so I'm going to say that's ugly. There's a much better way to calculate these residues, which I'm going to save to explain for next time. Better idea. Let's suppose I have f of z and g of z are analytic near, meaning they're analytic on a disk about A. So analytic near A. So that means on a disk about A. And suppose G has a simple zero. Meaning a zero of order 1. Meaning G of A is equal to 0, but G prime of A is not equal to 0. Then the formula is very convenient. The residue at A of f over G is equal to f of A over G prime of A. Very simple to calculate. Put that in a red box. Much easier to calculate. And so, for example, if you look at the thing we were just thinking about, let's write 1 over z to the 4th plus 1. The f of z is going to be 1. G of z is going to be z to the 4th plus 1. And notice that we know that the R1 is a root. So that's 0. And let's calculate G prime of z. G prime of z is 4z cubed. And so G prime of R1 would be 4 times R1 cubed. That's not equal to 0.